Welcome to the Deep Dive. Today we're heading out into the cosmos, taking a closer look at galaxies. You've got this great overview ready for us.
That's right. And our mission today is really to unpack the most, fascinating bits about them. Hopefully leave you feeling pretty clued in and maybe even eager to learn more.
Sounds perfect. Where are we drawing from mainly?
Our main source is the Wikipedia article on Galaxy. It's surprisingly comprehensive. Covers everything from the basics, what they are, the different types, right through to how they form, evolve, and, build these huge cosmic structures.
It even gets into the history of how we figured all this out.
Exactly. The history of observation, current research, it's all in there.
Okay, great. So let's start right at the beginning then.
Yeah.
What is a galaxy, fundamentally? When you look up, it's hard to grasp the scale.
Well, at its simplest, it's a huge system held together by gravity. Think stars, the leftovers of stars, like neutron stars and black holes, plus enormous clouds of gas and dust.
The stuff new stars are made from.
Precisely. And then there's the biggest component, which is actually dark matter.
Ah, dark matter, the great cosmic mystery. That really dominates, doesn't it?
It really does. Most of the mass in a typical galaxy isn't the stuff we see. It's this invisible dark matter providing the gravitational glue. We can definitely circle back to that another time. It's a whole deep dive in itself.
Good idea. And the word galaxy itself, that has a cool origin story.
It does. It comes from the Greek Galaxias, which basically means milky.
Ah, like our own Milky Way.
Exactly. A direct reference to how our galaxy looks as that band of light across the night sky.
And they vary hugely in size, I gather.
Oh, massively. You've got dwarf galaxies with maybe only a few hundred or 1,000 stars, like tiny cosmic villages.
Wow, that's small.
Yeah. And then you go all the way up to supergiant galaxies with, get this, hundreds of trillions of stars, all orbiting a common center.
Hundreds of trillions. It's just staggering.
Yeah.
And you said most of the mass is dark matter?
That's the current understanding, yes. All the stars, gas, and dust we can detect make up only a small percentage of the total mass needed to explain how galaxies rotate and hold together.
And it seems like supermassive black holes at the center are a pretty standard issue for the big ones.
It certainly looks that way. The evidence keeps growing that most, if not all, large galaxies, including ours, have a supermassive black hole lurking right at their core. They play a big role in the galaxy's evolution, too.
Okay, so gravity, stars, gas, dust, loads of dark matter, and often a giant black hole. Got it. Now, when we actually look out there, they don't all look the same, do they? We see different shapes.
Not at all. That's where galaxy classification comes in, based on what astronomers call their visual morphology, basically, their shape.
The main types being?
Elliptical, spiral, and irregular. Those are the big three categories.
Let's start with ellipticals. They sound kind of smooth.
Yeah, they are. They look like smooth, oval, or sort of football-shaped collections of stars. They don't have much obvious structure like spiral arms.
And they're mostly older stars.
Generally, yes. They tend to have less interstellar gas and dust, which means not much new star formation is happening. They're kind of the settled, older population of the galaxy universe.
Okay, then the spirals, the classic postcard galaxy image, right? Like our Milky Way.
Exactly. Spirals have that rotating disk structure, often with a central bulge of older stars, and then these beautiful spiral arms sweeping outwards.
And the arms are where the action is. Star formation.
That's right. The arms are density waves, basically, regions where gas gets compressed, triggering lots of new star birth. That's why they often look brighter and bluer.
And the last category. Irregular.
Yeah, these are the galaxies that just don't fit the neat elliptical or spiral patterns. They often look kind of messy without a clear shape.
Maybe they got disrupted somehow.
Often, yeah. Gravitational encounters with other galaxies can really mess up their structure. Or maybe they just never settled down into a regular form in the first place.
Okay, so those are the basic visual types. But figuring this all out took centuries, didn't it? It started with just trying to understand our own Milky Way.
Absolutely. Even the ancient Greeks were pondering that faint band of light. Democritus, way back, actually suggested it might be made of distant stars, which is pretty amazing foresight.
But Aristotle had a different idea.
Local.
Much more local. He thought it was some kind of atmospheric phenomenon, like a fiery gas igniting high up. Shows how influential figures can sometimes lead thinking down a different path for a while.
And that debate continued.
It did. Later thinkers like Olympiodorus argued it had to be celestial because it didn't show parallax. It didn't seem to shift position as the Earth moved.
Then came scholars in the Islamic Golden Age. What did they add?
Some crucial steps. Ibn al-Haytham tried to measure its parallax and concluded it must be really far away. Al-Biruni described it as like countless fragments of nebulous stars getting closer.
Wow. And others like Avem Pace and Ibn Qayyim?
Avem Pace suggested it was lots of stars packed so close they looked continuous, maybe due to atmospheric effects. Ibn Qayyim also described it as a huge number of tiny stars packed together way out in space. You can see the idea gradually firming up. It's incredible progress, just using naked eye observations.
Yeah.
But then, boom, the telescope. Galileo must have been pivotal.
Completely game-changing. 1610, he pointed his telescope at the Milky Way and resolved it into countless, faint, individual stars. That pretty much settled the debate about it being atmospheric. It was definitely made of stars.
And then people started thinking about its shape.
Mm-hmm.
Thomas Wright had some interesting ideas.
Very insightful. In 1750, he theorized it was a rotating disk of stars, like a giant solar system, and that our view from inside that disk is why it looks like a band.
And Kant built on that.
Yes, Kant elaborated on Wright's model just a few years later, picturing this flattened, rotating system. He even speculated that some of those fuzzy nebulae might be other island universes, other Milky Ways.
Island universes, that's a great term. But actually mapping our own galaxy proved tricky.
Herschel tried.
William Herschel made the first real attempt in 1785 by counting stars in different directions. But his map put the sun near the center, which we now know is wrong.
Why did he get that wrong? He didn't account for all the interstellar dust blocking the view. It makes distant stars look fainter or hides them completely, especially in the plane of the galaxy. Kapteyn later made a similar error, mapping a smaller galaxy with the sun near the center.
But Harlow Shapley got closer, using globular clusters.
Yes, Shapley studied globular clusters, which orbit the galaxy mostly outside the dusty plane. His work showed a much larger, flatter disk with the sun way out from the center. A major improvement, though still not perfect because of that dust issue.
Pesky dust. Who finally nailed that down?
Robert Julius Trumpler in 1930. He carefully studied how dust absorbed and reddened the light from star clusters, allowing astronomers to finally correct for it and get the modern picture of the Milky Way's size and our place within it.
Okay, so while we were figuring out our own galaxy, what about those other nebulae Kant speculated about? When did we realize they were separate galaxies?
Well, some are visible to the naked eye Andromeda, the Magellanic Clouds, Triangulum. Al-Sufi, a Persian astronomer, noted Andromeda as a small cloud way back in the 10th century. So they weren't unknown, just misunderstood.
Right, and people like Swedenborg and Wright started speculating they were other island universes.
Exactly. The idea gained traction in the 18th century. Maybe these fuzzy patches weren't inside our Milky Way at all.
And cataloging them helped, Messier and Herschel.
Definitely. Their catalogs created an inventory. Then Lord Rosse in 1845 saw the spiral structure in M51, the Whirlpool Galaxy. That was a huge clue. These things had definite shapes.
But seeing a shape isn't proof of distance. How do we confirm they were truly separate galaxies?
Spectroscopy was key.
Yeah.
Vesto Slipher, early 20th century, measured the Doppler shifts of these spiral nebulae. He found they were moving incredibly fast, mostly away from us, much faster than anything within the Milky Way.
Like seeing cars speeding away on a distant highway, not local traffic.
Exactly. And then Heber Curtis observed novae exploding stars in Andromeda. They look much fainter than novae in our galaxy.
Implying they were much further away.
Precisely. Curtis became a big proponent of the island universes idea. This led to the famous Great Debate in 1920 between Shapley, who argued for a larger Milky Way encompassing everything, and Curtis, arguing for separate galaxies.
A real scientific showdown. Who won?
Well, history sided with Curtis. Ernst Eppich provided a distance estimate supporting Andromeda being external. But the knockout blow came from Edwin Hubble.
Hubble, using the big Mount Wilson telescope.
Yes. He resolved individual stars in Andromeda and other nebulae. Crucially, he found Cepheid variable stars.
Those are like standard candles, right? Their pulsation tells you their true brightness.
Exactly. By comparing their true brightness to how faint they appeared, Hubble calculated their distances. And they were millions of light years away, far beyond the Milky Way. That settled it. They were indeed other galaxies.
Mind blown. The universe just got infinitely bigger. And Hubble didn't stop there. He classified them.
Right. In 1926, he published his classification scheme, Ellipticals, Spirals, Barred Spirals, based on their appearance. The Hubble tuning fork diagram. It's amazing how well that visual system still holds up today as a starting point.
Incredible story. So for ages, we mostly saw galaxies in visible light. But now we use the whole electromagnetic spectrum. How does that change things?
It revolutionizes everything. Take infrared light. Dust blocks visible light, but infrared cuts right through it.
So you can see into dusty star-forming regions, right? Or the galactic center.
Exactly. And you can see very distant galaxies whose light has been redshifted all the way into the infrared by the expansion of the universe. You need space telescopes for a lot of infrared work, though, because our atmosphere absorbs it.
Right. What about radio waves? You said that was the first non-visual window.
Yes. Our atmosphere is pretty transparent to radio waves. Radio astronomy revealed things like the huge jets coming from active galactic nuclei AGNs, stuff totally invisible optically.
And the high-energy end. UV and X-rays.
They show us the really violent stuff. UV can reveal stars getting ripped apart by black holes. X-rays let us see the incredibly hot gas in galaxy clusters, and they're crucial for studying the accretion disks around supermassive black holes.
So each wavelength gives you a different piece of the puzzle.
Precisely. Visible light shows stars. Infrared shows dust and cooled gas. Radio shows energetic electrons and cold hydrogen. X-rays show million-degree gas and black hole activity. Put it all together, and you get a much richer picture.
Okay, fascinating. What about key areas in modern galaxy research? What's pushing the envelope now?
Well, one fundamental tool is the 21-centimeter line of neutral hydrogen.
That specific radio wavelength.
Yes. It's emitted by cold hydrogen gas, and crucially, dust doesn't block it. So you can map the distribution and, importantly, the motion of hydrogen gas throughout a galaxy using its Doppler shift.
And that led to discovering the bar in the Milky Way.
Among other things, yes. It's vital for mapping gas dynamics in our galaxy and others, especially distant ones.
Then there was a rotation problem in the 70s. Vera Rubin's work.
A huge discovery. She and her colleagues found that stars in the outer parts of spiral galaxies were orbiting way too fast, faster than could be explained by the gravity of the visible stars and gas alone.
Enter dark matter.
Exactly. The best explanation became these vast, unseen halos of dark matter surrounding galaxies, providing the extra gravity needed to hold those fast-moving stars in orbit, a real paradigm shift.
And the Hubble Space Telescope itself. Launched in 1990.
Absolutely transformative. Its sharp images helped confirm dark matter wasn't just dim stars, and those deep field images, just mind-blowing. Staring at a tiny patch of empty sky and finding thousands of galaxies, that gave us the first real census, estimating maybe 125 billion galaxies.
But that number's gone up since then, with better tech.
Significantly. Newer surveys, especially in infrared and radio that can see through the Milky Way's dust, the zone of avoidance, have found many more.
Yeah, the current estimate is?
A 2016 study, combining lots of data, suggested there could be 2 trillion galaxies in the observable universe. Maybe even more. Though some later data, like from New Horizons looking at the background light, suggests maybe not quite that many are contributing significantly to the overall light budget. The exact number is still debated, but it's vastly more than we can directly see with current telescopes.
2 trillion. Okay, my brain just melted a little. Let's dive back into the types again, but with more detail. Ellipticals first. We know they're smooth old stars. Any interesting subtypes?
Oh, yes. You have the absolute monsters, the type CD galaxies or supergiant ellipticals. They're the largest known galaxies, often found at the heart of big galaxy clusters.
How big are we talking?
They have this huge diffuse halo of stars that can stretch for millions of light years megaparsecs, far bigger than a typical galaxy's visible extent.
How do they get so enormous?
The leading idea is galactic cannibalism, basically. They sit at the bottom of the cluster's gravity well and merge with many smaller galaxies over cosmic time. They just keep eating their neighbors. This can lead to fossil groups where you see one giant elliptical dominating.
Wow. Any other weird ellipticals?
There are shell galaxies. These have these faint concentric shells or arcs of stars in their outer regions. About 10% of ellipticals show this.
Like ripples on a pond. What causes them?
Exactly like ripples. It's thought to happen when an elliptical absorbs a smaller disk galaxy. The interaction sends stars out in waves, creating these shells. AGC 39233 is a famous example with tons of shells. It's a snapshot of a past merger.
Cool. Okay. Spirals. We know the basics. Disk, bulge, arms. And most mass is in a dark matter halo.
That's right. The visible disk is just the tip of the iceberg mass-wise. The dark matter halo dominates and dictates those flat rotation curves Vera Rubin observed.
And the arms aren't solid structures, they're waves.
Correct. They're density waves. Think of a traffic jam. The jam moves slowly, but cars move through it. Stars and gas pile up temporarily in the wave, which triggers star formation, making the arms bright with young stars.
Got it. And Many spirals, including ours, have a bar structure in the middle.
Yes, barred spirals, SB type, are very common, maybe 2/3 of all spirals. The bar is a big structure of stars spanning the central region.
What does the bar do?
It's thought to be quite important dynamically. They can funnel gas from the disk towards the center, potentially feeding star formation near the core or even fueling a central supermassive black hole, making the nucleus active.
So the bar is like a cosmic fuel line.
In a sense, yeah. Our Milky Way is a barred spiral about 100,000 light years across maybe 200 billion stars, but its total mass, including dark matter, is much higher, maybe 600 billion solar masses.
Are there extreme spirals too, like the giant ellipticals?
There are superluminous spirals. These can be several times larger than the Milky Way, incredibly massive, and forming stars at rates maybe 30 times higher than ours. Real powerhouses.
Okay, moving to the other morphologies. The peculiar ones are shaped by interactions.
Often, yes. Tidal forces during close encounters or mergers can stretch and distort galaxies into really unusual shapes.
And ring galaxies, like cosmic donuts.
Yeah, they look like that. A bright ring of stars and gas around a relatively empty center. Hoag's object is a famous one. They're thought to form from a specific type of collision. A smaller galaxy plunging right through the center of a larger disk galaxy.
What about lenticulars? They sound like a transition type.
They are. They have a disk like a spiral, but no obvious spiral arms and not much gas or current star formation. They might be faded spirals that have used up or lost their gas. Kind of intermediate between spirals and ellipticals.
Makes sense. And irregulars we covered messy, no clear shape.
Yeah.
Like the Magellanic Clouds.
Exactly. Our nearest galactic neighbors are dwarf irregulars. They can be some structure or completely chaotic.
Then there are these ultra-diffuse galaxies, dim and spread out.
Yeah, they're weird. As big as the Milky Way sometimes, but with only like 1% of the stars. Very low surface brightness. Maybe they lost their gas early on somehow. Still a bit of a puzzle.
And finally, dwarf galaxies. Most common type, you said.
By far. They vastly outnumber the big guys. They're small, maybe 100th the size of the Milky Way, a few billion stars. Many are satellites of larger galaxies, like the dozens orbiting our own Milky Way.
Any interesting subtypes?
There are blue compact dwarfs, which are bursting with young stars, and ultra-compact dwarfs, incredibly dense. And studies of dwarfs around the Milky Way hint that even the smallest ones are dominated by dark matter, maybe pointing towards its fundamental properties.
Even the little guys hold big clues. Okay, let's talk interactions. Galaxies aren't isolated islands.
Definitely not. Interactions are super common and crucial for how galaxies evolve. Even a near miss can warp galaxies, pull out tidal streams of stars and gas, even trigger star formation.
And actual collisions.
Yeah.
Stars don't hit each other usually.
Very rarely. Space is mostly empty, even inside galaxies. But the huge gas clouds do collide, compress, and that often triggers massive bursts of star formation. And the gravity completely rearranges the stars, creating bars, rings, tidal tails.
Tidal tails, those long streams of stars.
Yeah, pulled out by gravitational forces during the encounter. The antenna galaxies are a fantastic example of a collision in progress, with prominent tails.
What if they don't just pass through? They merge.
Right. If they don't have enough speed to escape each other's gravity after the collision, they'll eventually fall back together and merge into one larger galaxy. This is a key way galaxies grow, and it often transforms spirals into ellipticals.
And sometimes it's not equal. Galactic cannibalism.
Yep. A big galaxy can tidally shred and swallow a much smaller one. The Milky Way is doing this right now with the Sagittarius dwarf and others. We see streams of stars in our halo that are the remnants of past meals.
Our galaxy has a hungry past. Okay, let's shift to the really energetic galaxies. Starbursts first, what makes them burst?
They're forming stars at an incredible rate, maybe tens or hundreds of times faster than the Milky Way, often triggered by mergers or interactions that compress their gas clouds.
But they burn out quickly.
Relatively, yes. They use up their fuel fast. The starburst phase might only last 10 million years or so. M82, interacting with M81, is the classic nearby example. They were much more common in the early universe.
Okay, then radio galaxies. They shoot out huge jets powered by
the central supermassive black hole, an active galactic nucleus, or AGN. Material falling onto the black hole powers these enormous jets of particles traveling near light speed, which inflate giant lobes of radio emission far outside the visible galaxy.
And some are giant radio galaxies.
Yeah, the lobes can stretch for millions of light years, like Alcyonius, which is 5 megaparsecs across. It's incredible. They're classified by shape and power, FRI and FR2 types.
And normal radio emission comes from supernovae.
Right, not all radio emission is from AGNs. Supernova remnants accelerate electrons too, creating weaker, more diffuse radio glows related to ongoing star formation.
Got it. So active galaxies, or AGNs in general, the power comes from the nucleus, the black hole.
Exactly. It's the accretion disk around the supermassive black hole that's the engine. Sieverts are lower luminosity AGNs where you can still see the host galaxy clearly. Quasars are the most luminous type, often outshining their entire host galaxy by huge factors.
Quasars are the really distant, super bright ones?
Yes. They're so bright we can see them across billions of light years back to the early universe. They look star-like because they're so far away. They were also key in discovering gravitational lensing. Markarian 231 is relatively nearby. U8Z1 is incredibly distant.
Are there other AGN types? Blazars, liners.
Blazars are basically AGNs where one of the relativistic jets happens to be pointing almost directly at us, making them appear extremely bright and variable. Liners have low ionization emission lines from their nuclei, could be weak AGNs or maybe related to star formation near the center. About a third of nearby galaxies show liner activity.
A whole zoo of active nuclei. Lastly, luminous infrared galaxies, LIRGs and ULRGs, bright in infrared because of
dust. Intense star formation heats up vast amounts of dust, which then radiates brightly in the infrared. LIRGs emit over 100 billion solar luminosities in IR, ULRGs over 1 trillion, often triggered by mergers of gas-rich spirals. They emit more energy in infrared than all other wavelengths combined.
dusty star factories, often born from collisions. Okay, let's switch gears. How do we measure how big these things are? They don't have sharp edges.
That's the tricky part. There's no clear edge, so astronomers use conventions.
Like angular diameter, just how big it looks in the sky.
That was the early way. Measure the angle, estimate the distance, calculate a size. But it depends heavily on knowing the distance accurately.
So isophotal diameter is better, based on brightness.
It's more standardized. You measure out to where the galaxy's surface brightness drops below a certain faint level, typically 25 magnitudes per square arcsecond in blue light, D25. It gives a consistent, though somewhat arbitrary boundary.
Okay. What about effective radius, or half-light radius?
That measures concentration. It's the radius that encloses half of the galaxy's total light. A smaller re means the light is more packed towards the center. Useful for comparing how compact galaxies are.
And Petrosian magnitude, used by surveys like Sloan.
Right. It defines a radius based on the brightness profile itself in a way that's less sensitive to distance or surface brightness dimming. Good for comparing apparent sizes across large samples of galaxies at different distances.
Then there's a near-infrared method, using surveys like 2MAS.
Yeah, near-infrared light sees older stars better and penetrates dust. So 2MAS uses an isophotal measure at 2.2 microns, Camiha span, to trace the bulk of the stellar mass more effectively than optical methods. It uses a specific brightness level, 20 megaarcsec2, and various apertures to capture the light.
So different methods for different purposes, basically tracing different components. Now, zooming out again.
Yeah.
Large-scale structure, galaxies cluster together.
Oh, yeah, they're very social. Only about 5% are truly isolated. Most live in groups or massive clusters.
Gravity overcoming cosmic expansion locally.
Exactly. Gravity pulls them together into groups first, which then merge to form clusters over billions of years. These clusters are filled with incredibly hot gas, millions of degrees, that we see in X-rays.
And clusters are mostly dark matter.
Yep, 70-80% dark matter, 10-30% hot gas, and only a few percent in the galaxies themselves. Groups are smaller collections, the most common environment. Clusters are the huge ones, hundreds or thousands of galaxies, often dominated by a giant elliptical at the center.
And these clusters form even bigger structures, superclusters.
Right. Clusters and groups are arranged in vast filaments and sheets surrounding huge empty regions called voids. That's the cosmic web. Superclusters are these massive congregations. Above that scale, the universe looks roughly the same everywhere.
Mostly.
Well, structures like the Hercules Corona Borealis Great Wall, spanning 10 billion light years, really push the limits of how large structures should be in a perfectly homogeneous universe. Still debated.
Wow, and our local group is part of this.
Yep. We're in a small group dominated by the Milky Way and Andromeda, with lots of dwarf companions. We're on the edge of the Virgo supercluster, which is part of the even bigger Laniakea supercluster, our cosmic address.
Amazing. One more physical aspect. Magnetic fields. Galaxies have them.
They do. They're weak compared to Earth's maybe microgauss level, but they're there and they're important.
How so?
They influence gas dynamics, maybe help shape spiral arms, and critically, they help transport angular momentum out of gas clouds, allowing them to collapse and form stars. So they're tied into star formation.
Stronger and more active galaxies.
Generally, yes. Gas-rich, high star formation galaxies tend to have stronger fields, maybe 15 microgauss. Starburst galaxies can have fields up to 50 or 100 microgauss, likely amplified by all the turbulence.
Fascinating invisible influence. Okay, finally, let's tackle the grand narrative. Formation and evolution. How did the first galaxies get started?
According to the standard SCDM model, it began with tiny density fluctuations in the early universe right after the Big Bang. Dark matter started clumping together first, forming gravitational wells or halos.
And normal matter fell into these dark matter halos.
Exactly. Hydrogen and helium gas fell in, but it had to cool down to collapse further and form stars. This happened after recombination, about 300,000 years post-Big Bang, when the universe became neutral.
So gas collected in rotating disks within these halos.
Right. And eventually, density and pressure got high enough in spots to ignite the very first stars, population 3 stars.
Made of just hydrogen and helium.
Pretty much. Pure primordial gas. They were likely very massive and short-lived. Their intense UV light helped reionize the universe, ending the cosmic dark ages.
And when they died, they created the first heavy elements.
Yes. Their supernova explosions seeded the surrounding gas with elements heavier than helium, what astronomers call metals. This enriched gas then formed the next generation, population 2 stars, which have low but non-zero metallicity.
And we try to observe these earliest stages with JWST and others.
It's a huge focus. Trying to find light from those first galaxies and maybe even the first stars. It's cosmic archaeology, piecing together clues from the very faint, distant universe. Extremely challenging work.
So after those initial stages, how do galaxies evolve over billions of years?
It's complex. Gravity, gas flows, star formation, feedback from stars and black holes. Within the first billion years, you see key structures forming. Globular clusters, central black holes, stellar bulges. The black hole's growth seems tied to the galaxy's growth.
And they keep collecting gas and merging.
Yes, they accrete gas from intergalactic space, high-velocity clouds, and merge with smaller galaxies. This builds them up over time. Star formation continues, gradually enriching the gas with heavier elements.
Do interactions remain important?
Absolutely. Mergers were more common early on, shaping many galaxies. Even now, interactions influence star formation rates and morphology. The Milky Way Andromeda collision is a future example. Our galaxy has merged with others before, like the Kraken galaxy billions of years ago.
But major mergers are less common now.
Yes, as the universe expands, most big galaxies have been relatively stable for billions of years. The peak era of star formation across the universe was likely around 10 billion years ago.
What about the very, very distant future? What happens when the stars burn out?
Well, star formation will eventually cease as the gas runs out or gets locked up. Spirals keep going as long as they have gas. Ellipticals have mostly stopped already. This star-forming era might last another 100 billion years.
After that,
the stellar age ends. The longest-lived stars, red dwarfs, will finally fade after trillions of years. Galaxies will become collections of stellar remnants. White dwarfs, neutron stars, black holes, brown dwarfs.
the galaxy of ghosts.
Pretty much. And over truly unimaginable timescales, far, far longer than the current age of the universe, gravitational interactions will cause most of these remnants to either fall into the central supermassive black hole or get ejected from the galaxy entirely. A slow, quiet end.
Wow. An incredible journey from the Big Bang to that. We have covered an immense amount of ground today. From the basic definition to types, history, interactions, extreme activity, how we measure them, their place in the cosmos, and their ultimate fate.
It's a vast topic. We've really only scratched the surface, but hopefully it gives a good sense of what galaxies are and how we study them. From Democritus pondering the Milky Way to JWST peering back towards the cosmic dawn.
Absolutely. And thinking about potentially trillions of these structures, each with billions or trillions of stars, and the dynamic interplay between them, it really puts things in perspective. It makes you wonder, what else we're missing? What other forces or processes are shaping them that we don't even know about yet?
That's the beauty of cosmology and astrophysics, isn't it? There are always more questions, deeper mysteries to unravel. And for you listening, if any of this sparked your interest, the Wikipedia article is a great starting point. But definitely follow the links and references. Maybe dive deeper into barred spirals or quasars or galaxy formation models.
For sure. This deep dive is done, but the universe is out there waiting to be explored further.